This video uses a function from sets and probabilities. We load the three functions into our calculator. Switch our calculator over to CAS view. Highlight the first function. Double click, shift click, Control C to copy, go over to our calculator, Control V, paste, press enter. Here our calculator screen shows the other two functions being added. You can find this code by going back to the info immediate mode and then hitting finite math. You will see this code shown. We now load Onenote to look at set algebra. We have switched our HP prime calculator screen over to the complement screen. First, we put in L1 to be 1, 2, 3, and 4. L2 to be 3, 4, 5, and 6. L3 to be 7, 8, and 9. So what we're talking about here is L1 is A, L2 is B, and L3 is this area in the white for our universal set. Using the HP prime union command with L1, L2, and L3 sets up our universal set. Then if we take the complement of the empty set with the universal set, we end up with the universal set. So if this is shown over here in our table. The next thing we work on is the third entry, where the complement of A is equal to A. So we take the complement of L1 with universe, which is equal to L4. Then we take the complement of L4, which we get back to A. The last two entries in our table have us do the intersection of A with the complement, which turns out to be the empty set, and then the union of L1 with the complement, which turns out to be the universal set. We find these commands by pressing the toolbox key, pressing the list operator, using reverse scroll to find our union and intersection commands. The complement command is the function that we added, is found by pressing the var key, pressing 2 for program, and then pressing 1 for complement. We have switched over our calculator to the second screen that has to do with the operation table. For the first two entries in our table, we use the same L1, L2, and L3 that we did in the complement table. We take the union and the intersection just to show what the values are before we do the first two entries in the table. The first two entries in the table are done by setting intersect of L1 and L2 with the intersect of L2 and L1. We have to use the sort command to put this into the same order that we have here. When we set this equal, what they're saying is we get two entries, and the two entries are both ones, so this is saying that it is true. In the union, again, we have to use the sort command. Here we get our 6 entries. They again all turn out to be 1, so that this means that they are true. What these ones mean is that 3 is equal to 3 and 4 is equal to 4. Here, 1 is equal to 1, 2 is equal to 2, 3 is equal to 3, 4 is equal to 4, 5 is equal to 5, and 6 is equal to 6. So that's how come we come up with so many ones when we compare the two with the equal. We are using the Boolean operation, and true is 1 and false is 0. We now switch the screen to A, B, and C so that we can do the last 4 entries in the table, it requires that we work with A, B, and C, or L1, L2, L3, and L4, which is the numbers in the white outside of A, B, and C. We have switched the screen over to show that the associative property holds for intersection. The first 2 lines in our screen here are A and B and C. So we store these as L5 and L6. By first 2 lines, we mean after we set the problem up. These are the first 2 lines. Then we take the answer that we have here, which is L5, and combine it with C, and we take A and combine it with the answer that we have here, which is L6. So we're talking about where all 3 of these things are in common, which would be this center area, which would actually be the element 4. So when we do the equal sign, there's only one element we're comparing, and the 4 is equal to 4, so that's why it turns out to be true. We would use the same procedure to show that the associative property holds for union, and to show that we have the distributed working for intersection and the distributed property for working for union. There are 2 more important rules for set algebra called De Morgan's law, so let's switch to that subpage. We switch our HP prime calculator over to De Morgan's law. The table over here shows us the first De Morgan's law is that when we take the intersection's complement, it is equal to the union of the complements. The second one says when we take the union's complement, it is equal to the intersection of the complements. We start off by setting up our initial problem and taking the union and the intersection of the sets L1 and L2. We're actually going to use the union, for the second law. The intersection we're going to need for our first law. What we do for our first diagram is we take the complement of the intersection. So when we go over to our screenshot, this will take 2 commands. So we take the intersection of L1 and L2 and store it as L5. Then we take the complement of the universal set with L5 and store it as L6. So this is what is shown in the first Venn diagram. Scrolling to the last part of our De Morgan law screen, we now look at the code for these last 2 Venn diagrams. By code, I mean the commands that we put into our HP prime device. L7 is the complement of L1 or A. L8 is the complement of L2 or B. We join both the left and right drawings on our HP prime by using the union operation. Then we use the equal to compare L6 and L9, and it turns out that these 2 are false. We put the sort on top of the union, and then it turns out that these 2 are equal, or 1. So we must sort before we compare with the equal. The equal command is found by pressing the toolbox, pressing list, reverse scrolling, and we see the equal command. Use the same technique to verify the second De Morgan's law. This ends our video on set algebra.